Okay, let's begin. So for th- for this Python primer, we're gonna be looking at source panel method. I guess just to quickly catch our speed, let me talk about why or what we have done 2 weeks ago and why this Python lesson right now is relevant. So last week, using our knowledge of potential flow and superposition, we tried to superimpose a free stream and like 4 or 5 different sources to create a NACA 0012 airfoil. And then we try to capture the surface distribution along the airfoil. As you see from our results, this is not what a typical CP plot would look like. You expect to start positive, which is at the bottom, spike upwards, then come back down as it dissipates. But obviously, as you see here, all we have is it starts negative and then it quickly drastically drops down. We don't see any positive CP values at the leading edge. So obviously, this method, while we are able to capture some trends such as the dissipation of, the dissipation of the negative CP on the suction side, it is not complete. It's not fully accurate. Therefore, this week we'll be using the source panel method that Professor Robinson has discussed in class in order to capture these pressure distributions. We're going to focus on cylinder because it's very much the most simple geometry, and we have an analytical solution for this. But at the very end, I'll show that how it can be applied to different other airfoils. Quick side note, exactly a year ago, I didn't realize, but I was about to go trick-or-treating, same costume, I know. But then Professor Robinson, he emailed me and he said, can you take over the class for me for a day? And I was like, I can't say no to this, can I? So, in my costume, I pulled up, and then that was, you know, while I want to say I did a good job, I didn't really understand source panel method that well back then. So I really butchered my explanation of it. But hopefully, this time around, I can give a better explanation for the rest of the class to use. Okay, so let's start just really simply. We have a cylinder, that's our geometry. First thing we want to do for any numerical, or I guess any numerical process, which is what this class is kind of like, yeah, is we want to discretize your geometry. What I mean by that is obviously your geometry has an infinite amount of points. We're going to look at, we're going to take a cylinder, cut it into 8 different panels. To do that, we need 9 nodes. So we'll have our 9 nodes around the cylinder, starting from 0 degrees, which is the rear of the cylinder, and we're doing increments of 45. Every increment of 45, we'll put another node or point. Therefore, we'll have 9 points around geometry, and the last point and first point are overlapping each other. Once again, because we have 9 points, every adjacent point then becomes a panel. As a result, from 9 points, we'll have 8 panels, and I have listed some values here, but as you see, values we care about in terms of our geometry is as follows. For each point, we care about its I guess basically its angle and its radius, but because we're working Cartesian coordinates, we turn radius into x and y coordinates. Essentially, the angle of the coordinate, the angle of the point and its x and y position. That's what we care about. From those 3 different values, we can extrapolate a lot of different parameters for our panels, shown on the right table. So from there, we get center points of the panel by taking the average of your x and y values from your points. You get this the center points of your panels. On top of that, by solving for the hypotenuse, you can obtain the length of each panel. And finally, beta I refers to the normal angle of the panel. Say for instance, like we have the ground, the normal direction would be straight up or 9 degrees, right? And for a panel like sideways or vertically, your normal would be 0 or pi. So that's what the beta term stands for. It's just the normal incident with your panel. So at least in terms of the code, in the very first block and right underneath like some very basic, like 4 lines into the code, you'll see the following code on the left-hand side. It says class panel. So at least in the homework and this code currently, we're just looking at 8 panels. But there are cases where, of course, like for example, Xflow, which is an example of a vortex panel method solver, you can have up to like 400 something points, 500 different panels, right? Therefore, it's really important to classify each panel. So you don't call panel 1, panel 2, panel 3. You classify them into the class. So you can basically organize all the different data for each panel into just one kind of like block. So as I said before, what is relevant for each panel is obviously its X and Y it's I guess this X and Y start point, X and Y end point, which are the points I discussed earlier, followed by the center point of the panel, the length of the panel, and the normal incident angle of the panel. The three other values on the bottom, sigma, VT, and CP, we'll discuss more later, but just know that that is what we're calculating for by the end of this code. That's kind of like the point of this exercise. Okay, so let's talk about source panel method. I think the main condition that is being fulfilled by the source panel method is basically it's called no penetration. And long story short, in blue here, we see your streamline, which is representing flow flowing around your geometry. And the most important streamline is the red streamline. That's your define streamline. The define streamline defines your geometry, it defines your shape in this potential flow. And so those are the blue and red lines. Now look at the light green line. The right green line is called velocity potential. So the streamlines, which are blue, or which are the blue arrows and the red line, those are streamline functions. So those are psi values. The light blue value, velocity potential, that's your phi. That's your phi value. So if you remember phi and phi from 103 and 106, there. So what makes the phi value unique is your velocity potential is, if you want the code, it's on the Canvas announcement. If you want velocity potential, or I guess all of your velocity potential lines are perpendicular to your streamlines. That's kind of like their whole dynamic. So streamlines show the flow, and velocity potentials are perpendicular to that. So therefore, if the light green lines are perpendicular to your streamlines, then by default, looking at the define streamline, the red line, all of your velocity potentials at those locations are like your normal directions. They give you the normal direction to that surface itself. So yeah, we can say that the potential lines can represent normal velocity with respect to the streamlines itself. Is the point. So that's why it's really important to look at that. And what I mean by that is this equation here. So Professor Robinson may have mentioned, UN, which is normal velocity, should be 0, because if it's not 0, your flow is going to penetrate the surface, or it's creating flow from the surface. That's the first line of the equation. So second line, you just break it down. The first term itself is simple and highlighted in blue. That's just your free stream in the flow field. It's just there. The next terms are more complicated, which is essentially just a summation of the different sources or different panels in play. In a way, you think of it as just doing superposition of different sources that we did in the previous code, but now it's a little more complex, and I'll talk about that more later. But let's see. If you look at the current setup here, you could set up this equation in terms of a matrix solver. Nice costume. So we have an A matrix, which is highlighted in yellow. We have your sigma surface, sigma, I guess, vector, highlighted in pink, and you have your B vector highlighted in blue. So essentially, we want to solve this system equations because we technically have all the values highlighted in yellow. We have all the values highlighted in blue, but we're missing the values highlighted in pink. And those are essentially the source strength represented with each panel. I'll talk more about that in a bit, but for now, just understand that A represents, panel geometry, all that kind of stuff. Blue represents free stream velocity, and sigma is this source strength for each panel. Okay, so once again, just to reiterate, we have 8 panels in this in our surface. We discretize it into 8 panels. So if we have 8 panels, we're gonna have an 8x8 matrix. Now it sounds bad, but let me just talk for a little bit. We're just gonna focus on the first row for now. So the first row is gonna be a row 1. So how the matrix works is, it's kind of like I think it's like row, comma, column, right? So A11, A12, A13, etc., all the way down. So what this means is the first element in your row is 1, 1, which refers to panel 1's influence on panel 1. It sounds a little bizarre, but the panel itself is gonna have influence on itself. The reason this is the case is because your panels are not point sources, which are what we dealt with such a flow currently when you superposition them. These are gonna be line sources. So something we see maybe in physics E&M potentially, line sources. We'll talk more about that later. Actually, but yeah, this is line source. And so let's go on the list. 1, 2 represents the influence of panel 2 on panel 1, panel 3 on panel 1, 4 on 1, etc. There's 8 panels, so there's gonna be 8 sources of influence on each panel. Something we gotta consider. That's why you have to solve it through a matrix and not just by an simple like system of equations. Okay, so there was like a lesson that basically covers this that I have time to go into, so I'll just kind of give you the kind of like the answer. The panel's influence on self can be represented by 1/2. This comes from the 1/2 showed by the sigma I over 2. You just take the 1/2, and that's why the influence is 1/2. But the other terms, you're gonna have to use the integral to solve for that. And so as I said before, so once again, subscript I represents the panel you're looking at. J represents the panel that's influencing it. So for panel I, which is what we're looking at, we're gonna essentially assume that all the influence is gonna impact it at the center of the panel. That's why it's important to get the center of the panel. However, for the panels that are influencing that panel, panel J, we're gonna consider that as a line source, which is what it is. And because it's a line source, every point in that line is a different distance away from the panel center. That's why we do integration to consider the influence of each infinitesimal segment of the panel on the center of the panel I. Doesn't make any sense. Panel J we represent as an equation to look at each different infinitesimal point. Panel I would just look at the center point. So one's a line, one's just a point. So maybe we run the first part of the code because the code I have here, that is the second block in the code that I just said. So the first block, just setting up the panel class and like some basic geometry like your cylinder, free stream velocity, those kind of things. The second part of the second block of the code represents some of the more tedious math that's involved. So that's that normal integral there. You can compare it to the equation I showed a few slides ago. They're the same. Once again, like I said, you're just looking to influence at each infinitesimal points in panel J on panel I. And basically what I explained in the previous slide, I rewrite here for you guys to look at later. Now let me go to the next part. So what I want you to do in homework 4 essentially is to hand do this. I know there's 8 panels, but once again, let's just focus on I know it's 8 panels, so there's 8 matrix, but let's just focus on the first line. So therefore, you have to do this 8 times, essentially. It's 8 times, you get a different value for each influence from each different panels. But by going to this integral, where panel 2 is highlighted in pink, panel 1 is highlighted in blue, you can get a numerical value. You're just solving an integral, a line integral. And so you get your points. Let's say you do this 7 times, so you get it for the entire row. So once you solve for the first row, you don't have to solve for the rest of the 7 rows because you have a symmetrical object. It's a cylinder. So what you can do, what happens actually, is your matrix turns into a periodic matrix. What I mean by that is all that happens between each different rows. When you look at the influence panel 2, the entire row just shifts by 1. That's highlighted in red. You can see from row 1, row 2 for the 8 matrix, it just shifts by 1. Because if we were to rotate, so let's say we move from panel 1 to panel 2, if we were to rotate the cylinder by like 45 degrees, panel 2 is just panel 1. Does that make sense? That's why you have a periodic matrix. And that's going to fall all the way down for the rest of the 8 columns. So you don't have to solve for the 8 by 8 matrix. If you do, I don't know whether to applaud you or laugh at you. You know what I'm saying? So just solve for the first row and then treat it as a periodic matrix. Okay. So last part, or our first part, we solved the A matrix. That's probably the hardest part. Now we just solve for the B vector. B vector, once again, is just free stream influence on each panel. I had the equation somewhere earlier. You can look at it, but it's very simple. It's just like free stream times sine and then normal incident angle of the panel you're looking at. That's just the equation it is. And then from that, you can solve for your array of sigmas, which is this source strengths. If you would run the second block of code for me, it will output what you should expect. It says vector A or matrix A should be this, vector B should be this, and sigma should be this. So when you do your homework 4, you should match those values that I have in code block 2. And I have the code posted on Canvas. Okay, any questions so far? I know kind of covered a lot, but I think this definitely is the biggest part of source bound method. Understanding that velocity potentials are normal velocities to your surface, then going through a process to essentially maintain that boundary condition that normal velocity should be fixed at 0. And then from that, you calculate the strengths of each respective panel to obtain that boundary condition or to meet that boundary condition. Sounds good? Obviously, there's more nuance that I explained earlier, but it's kind of the gist of step two. So you obtain all your surface strength. That's good. Like once again, that's probably the hardest part, maybe. But for that, what I want you to do is obviously I want to do some post processing. Show me that what you got means something, like it works essentially. So how do we do that? Obviously, we have a cylinder. Cylinders have a analytical solution for coefficient of pressure or pressure distribution. We're going to be trying to calculate that for our case and match it to the solution for potential flow. So we can calculate coefficient of pressure by looking at the tangential velocity. We've done this in the previous Python lessons. We're just doing it again now. So to obtain the tangential velocity, you take you just once again you look at the potential velocity. Okay, according to my writing, you derive the potential velocity with respects to the tangential direction. I think you can do this with just deriving psi instead of phi. I believe it's kind of the same thing, but that's why I saw from the code. And when you do so, you're obtaining the new expression here. I think it's well, actually, it's mostly similar to be honest, with the exception of a few things. There's some sign changes in the integral. That's one of the biggest change. But the second big change is that there was a sigma I over 2 that was like really insistent on earlier. Remember that? We don't consider the influence of the source itself now when it comes to calculating tangential velocity. I believe it's because when we look at like I said, we're taking instead of taking the normal derivative to your panel, you're taking the tangential derivative, which is like an orthogonal derivative, and therefore that term just goes away from doing that. That's kind of like the long and short of it. But as a result, we get a new matrix, and instead of trying to solve for a vector by like having to like basically do like I don't know where it is. Basically, you have to invert the matrix to solve for sigma. You don't have to invert any matrix anymore. You just plug and chug more or less. And this plug and chug is just your V term highlighted in blue from the free stream influence plus A, which is your like the cylinder geometry, all the surfaces, all the stuff, multiplied by sigma, which is what we solve for, the source strength of each panel. And doing so, you can basically solve for your tangential velocity at each panel. So as you saw earlier in like one of the earlier slides, it said in the class panel, we had a section for sigma, we had a section for VT, and we also have a section for CP. This is where it comes in. So we basically run the code for block 3 in the code I sent you. And once again, we have to update our function because it's not a normal integral, it's a tangential integrand. So, we solve that. And with your VT, you can then solve for coefficient pressure by we basically rederive Bernoulli's equation to obtain the following expression. 1 minus VT over V free stream squared gives you CP. So, doing so, what do we get? Sorry. You'll see that your solution looks for the analytical solution. The source panel method does a very, very good job at solving for it. Once again, this is potential flow. There's no like viscosity or like parasitic drag occurring. But once again, it captures something very similar to the analytical solution. And you might ask, well, who cares? Because when we put like the doublet in free stream, we get the exact same result. So why would we care about this method? And like I said, you remember from the very start of the presentation, I showed you the results when we tried plotting for NACA 0012 airfoil. When we do so with source panel method, you'll see that our results match very, very, very well with XWell results. I don't remember what exact cases was. I think it's angle of attack of 0 at some free stream velocity, obviously in viscous case. But we basically perfectly match what is expected from XWell. And once again, this is what XWell kind of runs on. This is this type of code that XWell uses, Vortex source panel method. But this kind of a simple version of that. And with that, once again, I want to give a huge thank you to the professor who made this Python lesson. It's Dr. Lauren Barra from Boston University. If you ever want to access the code, the link is always right here for you to look at. And yeah, that's my lessons for source panel method. Any questions?
I just wanted to confirm. So the method we use here where the matrix only has to solve like the row, and then we could just like kind of move it down as you went. like you just shift it. That's only because the cylinder is symmetric.
Yes.
But if we're doing like a more complex geometry, we'd have to solve each row like on its own and then put it into the A matrix.
Yeah.
Okay.
So, luckily we're looking at some geometry, but
Yeah.
otherwise you need Python code. Or do by hand, right? Prove me wrong. James.
I remember you said we have to that panel I to J calculation 8 times. And I was wondering, is that like integrating over like an area, and then combining everything? Or is it like each individual area is like its own separate component?
Are asking like me solving for like each part in that row?
Mhm.
Okay,
So could you run through that again?
sure. And then here's the best part.
Okay.
Essentially, that integral, what we're looking at is obviously we're looking at influence of panel J on I. Unfortunately, I don't have the color coded here. It's on the next slide, but so panel J and panel I. Every panel is a line source. So if you want to think about it, once again, back to E&M physics, not really my favorite class. I really actually did not like the class at all. But each panel is a line source, meaning every single infinitesimal point on that line is like that source strength. So
Okay.
yeah, so therefore, and we're gonna treat panel I as just a point. So therefore, every infinitesimal point along the panel J has a different distance away from panel I. And we want to consider the influence of each infinitesimal point on panel J on I. That's why I do an integral.
Okay.
Does that make sense?
Yeah.
Okay, let me go to you.
So A doesn't include the inputs of the free string, right?
No, no. Potentially the vortex, like the upgrade version, I think it does. I gotta double check, but for those,
But the influence of the free string would change along the cylinder, right? So you couldn't do the.
so it's still in a way building blocks. They're all kind of separate building blocks, and the building block for free stream is gonna be free stream. Like the influence is calculated afterwards as you solve the tangential velocity. That's not affecting free stream. Free stream is still itself. It's still its own building block. It's not being affected. That's when you calculate for tangential velocity. We consider all of those influences. Okay. Yeah, once again, just to quickly reiterate. That's the blue part. That's just free stream influence. It's just the blue part. Okay. Well, hopefully this helps you. The homework, I will be posting everything on Canvas to access the code, slides, not the solutions, but yeah, sounds great. Thank you.
Thank you.
Mhm. And if there's any other questions for homework from this week, homework 3, I'll be happy to answer it as well. And feel free to grab some treats from the I bought this for you guys.
Slides on Canvas.
Not yet. But I will post them soon.
Like Telegram, or is it-
Make sure the question two by homework, which to not show the application, right?
Yeah. Right. I think I said it was really poorly worded. It was like explain why no boundary layers are irrotational, which just means explain that they are rotational. But yes, prove that it's rotational.
Then it also said like the equation for irrotational, like.
Oh,
so-
I said equals 0.
Yeah,
I should have said not equals 0. Yeah, that's what I meant.
Wait.
Hmm?
Question for the studies. Yeah, you do the. So.
Like our panel systems, like
Yeah, so panels, they want some more for sure they fill in to when I run for.
by definition of boundary layer with varies the trace velocity varies are either.
Sorry.
Oh, it's trace velocity is how.
I just.
A rapid
Days. Sometimes.
Oh.
For P, it's. You get for. One side. He looks so.
Yeah, it's more difficult. I just he was yes, not as bad. Obviously, I expect the for bunching, the more bunching you have in your front, it should be better because all the effects mostly occur in strong edge. But I didn't really maybe no, honestly, I thought the plot or because I think if you put one, you're getting both channels near the mid core,
Yeah.
which obviously there's still some effects going on. I think maybe that's what. But obviously, you see, at least for Lynn, you see it starts to do outside of nature. Starts to look like a stroll. Out of plot, like certain for this, the man, it's stuff like it. And so for myself, right, with the I don't know.
Yeah, there's
We're clutching. Was last forever? I can't remember last forever. Was it leading the Jesus goes an elevation? Maybe I don't say distribution. I think it's moving to that feature. Yeah.
because I missed yesterday.
Right.
And so like
I think
thought to know to a short he was friends.
I interpreted this as like
I've been read to a question,
the default value was fire. Gives you those
but
sort
sort of this
in terms of and that's the
this is
or I guess I wasn't too sure if I'm sure the front of the car. That's fine.
Yeah.
My
They're my friends.
Trying.
Yeah, this is last.
That's the important is this.
dark line.
They still do the intro where they play like Metallica when they walk through the head, right?
Yes.
I can't remember it. Listen.
But I've never been to a hockey game where I feel like
Right.
like
But,
I said, yeah, sure.
No, yeah.
And so we're
You-
doing around like we're gonna do like the trike game like during the
Austin one, but
yes. Like when you
downside both sides. I just.
But they-
I was expecting
oh yeah, they like
more out
they
of the leading hands.
so
So
that was
better.
oh that's great.
I guess they're actually.
Well, even though
Almost give the weight current I'm trying it, but my understanding is how Expo works is that it's just predicting a weight.
I learned
the weight.
I learned this. So I watched the really lost.
I believe the lower the value, the more much you have to try or the leading edge to try.
So
But you learn.
well because I was because the handlebar
That's
so
so
low,
excessive.
I couldn't like I tried pedal from I was so like also like this, but then I like leaned forward into like going up like all here. So I could actually like that's when I could like so like big
That's why, but also
no, but that's it was
the
so
more
much.
perfect for
That was like right.
maybe that's last. Yeah. Or is it
It was great. Definitely gonna be like that every time I go.
one? Yeah, it's so I did the boat, like I'm seeing it's still the same line I did brought no pleasure. I have
So for
the
the
documentation, but
black, do you think you would split it up into your handles? I know there's
or my
for
answers.
number six. Yeah, do you think I split it up into like the
Lower
radial
But if at one,
like
they have there's
like
a lot more on both sides. Then I expect it's better.
yeah.
But if
Good eye show is fine.
so on the. Because I think the number of known panels are still static. So it's just maybe taking away from lineage. That yes. Sounds good. Okay, I think that's fine. Okay, that's interesting. Yeah, thanks for sharing. Yeah, it's a good question.
The errors on
Yeah. So this should be not zero, but I was just showing the equation for irritation value because that's what I was thinking about the time. But I was trying to show it's not the zero.
Thank you.
Yes.
Also, quick question. So the idea, I don't have Expo. What's this?
Okay.
I made my plot. I had kind of
I was thinking like Q plot or something for Expo purposes, but I can't know what it's called. Yeah.
these plot this was fine from it.
Yeah.
Do you have any idea why? Yes. One of these was split in turn. Like you came into volume. I think it might have been this oh.
You're saying flip in the axis?
No, the trends. So one
Trends.
trend.
So I see Fox in this case through sense.
Yeah.
So here, the reason why.
Yeah, sorry, is this one?
So the reason why Fox is higher is because your angle attack range is shorter.
Mm.
Your shorter angle attack range. So you need to capture that downwards part. That's where the most direct curves. Like that drop off. You don't have a drop off there. dedicated, it was just like for the collaborations, yes. Was it cause like it's like error, like not perfect?
S is the path.
Yeah, for at least
Right?
for when I was getting like the other side values, yeah. You can see how it's like an off for sure. No more than that.
I was just thinking,
That's what I searched, the officer study, much earlier than homework, some people don't use the power binder, you need admin panels.
I thought why not?
Make it like more.
The recording thing's very tough. These brought up like the probably like goes out as back right and
Or that as well.
Yeah, always some other way of doing it. It's like, oh, it's like, it's for them a lot.
I don't,
And around.
Very fortunate.
Yeah.
No, like that big deal, but maybe it will be in the future, I don't know. We'll see, yeah, I'm sure we've done one, yeah. Maybe.
Oh, go over like how you parameterize the line integral, like the path. I know would we keep it in Cartesian or would we have to do like separate for the like cylindrical path?
No,
We have to split up the velocity field and like the different directions. I'm just like I haven't done a line integral in like
Forever, right?
Yeah.
yeah, once again, this is like 9C physics and probably 21D, it's gonna be a very long time for sure. Let's see. This isn't done yet. Um. Okay, so obviously, like I said before, influence panel J on I, treat I as a point, and treat J as a line, correct? So, but therefore, the, and first of all, no, we maintain in Cartesian coordinates, and we don't consider influence flow field. It's like, it's just the panels itself with respect to each other. That's all we're looking at. The whole point of the A matrix and the sigma matrix is to make that geometry.
Yeah.
To make your geometry and make sure there's no penetration. That's all it's doing. So, okay, sorry. Channel J is the line source. Therefore, we treat it as a function because once again, each infinitesimal point of your line of the line's source, which is the panel, influences that panel J, the middle point, at different distances away. It's all the same strength, a lot of cool line, same strength but different distance away. So we treat it as a function. Function J, xj and yj is just the x and y coordinates along the line. We're written as a linear function because it's a line. So we have the starting index. Once again, we have to discretize as points, and then from points we get panels. Therefore, the panels remember what its start and end points are. So in the code will call on its original starting point of the panel. Then from that starting point, obviously, you take the normal index, but instead of with the normal index, you essentially switch the sign to get the tangential, like angle.
Okay. Yeah.
So you switch the trig function. So the normal you're looking at the tangential, and then we crawl along the panel in terms of the infinitesimal points s. So kind of like s like your like this just like the value your variable that you increase like at zero.
Each point basically like an index or like a value of s.
It's the
that
function.
follow along it.
This is the function, yeah. And that's why we integrate regressive s. And I think s at zero, obviously at zero, you should get starting points. And then at the max, which is 15. At the max, which is the length of your panel, which is L, you should get the other endpoints.
Okay.
I don't know, I didn't double check it, but that's how it works.
Yeah. So the panel method, like using the line integral here makes sense, like because it's if we keep it like Cartesian, like it makes sense like you integrate along the line and we can fairly easily find like where the points are. On the homework 3 though, I'm having a bit of an issue like
Circular integral?
yeah, like how to do that with because we want to do a circle, but also we're defining the velocity field in polar, and so I'm just like I don't know how to like if I need to split it up into like the different components and then deal with it that way, or if I just like how I parameterize the line so that it makes sense with regards to the flow field we have.
So these are two separate integrals. This one's just like a normal
Yeah,
integral, or it's a line integral, quote unquote, but
yeah.
you're just integrating across them. It's kind of function. So, the other one, is it called line integral? I thought
Or circular line integral. Yeah.
sorry, it's like path integral.
Sorry,
Sorry.
path.
I said it's a line source, so you're integrating for a line source. That's here.
Yes.
Integrating for a line source. Line integral is different. I'll show you what I use. It's like Paul's notes or something. Let me pull it up. Actually, before I do that, the easiest one is the easier one is probably the square. Sorry,
Yeah.
part B. Part B. Can you do part B? Do we have to do that one or?
I didn't give it a shot yet.
Sure. Long story short, your flow field there's U parameter and there's V parameter, right? So you have your man. Once again, this is why I hate EM physics. But there's a stupid problem. There's two parallel capacitors, right? So there's a flow field going through, and then there's a circle around it, and they're like, calculate the Gaussian flux on it. And so I'm here doing all this math, and I'm like, I can't figure this out. I can't figure this out. I remember that was the first time I ever like whited out in the middle of the class. I just like lost memory. But the answer was 0. Because every single, once again, parallel capacitor, every flux going through that circle is going out. So 0. But I didn't think about it at the time. I was trying to do the math, and the math was math. Now, not and you get 100% by just putting 0, apparently. That's so stupid. My point, that being said, I have a square, right?
Yes.
Obviously, hella flow going through it. But there's a U component, there's a V component. On my square, only the left and right side experience the U velocity. Because anything V velocity is going conventional to the sides, right?
Yes.
So you don't consider that. So for the U velocities, only consider the left and right side of your square. Same concept for the top and bottom. You only consider the V velocity. So in the way you can have break up the terms. So when you integrate for your left and right side, just consider U component. And I think you integrate with dy. I should double check that, but
Yeah,
For-
for Cartesian, you can keep it where it's like the y component needs to take derivative with respect to x, and then you take the x exponent and the y. So for the square line integral, you would get the flow field,
Mhm.
you get the velocity field in Cartesian. Would be the simplest way of doing that.
yes, for
Okay.
100%. And like I said before, left right side, look at U velocities, top bottom, look at V velocities, right? Because
Yeah.
that's the velocity that's going through. You're going through, that's going through. I think I converted to Green's theorem. That's why that's what I did. And what I did. For top and bottom sides, I integrate with respect to dx. I think it's because like once same concept. I'm crawling across the top and bottom surface. So obviously u along x, right? And for the side walls, the left and right side, crawling vertically for those two, right? So then I do dy.
Okay.
That's what I did. I need to double check if I just convert line integral into Green's theorem or not. Because I don't know. I just solved it how like intuitively. I'm like, oh, obviously you got to do all sides.
Yeah.
Sorry, I think I got reversed. You don't want to look at things going through it. Sorry for the analogy. You want to look at the velocities going along it. Sorry. You want to look at the velocities going along it. So for the side walls, look at the V velocity because going along it, not going through it. Same for top bottom.
Yeah.
Sorry, I got reversed. I'm thinking about flux. I'm like line integral is separate. I'm so sorry.
Yeah.
So your side velocity. So looking at line integral, right? Let's say I look at a vortex.
Which is the dot product.
Dot product. Yeah, sorry. I got mixed up. I'm looking at dot product. So on my side, my left and right side, I want the velocities along it because my whole point to see when I integrate around this whole thing, what is like the circulation or what is like that velocity combined. So sorry, left right side integrate with respects to v velocities, top bottom u velocity, but same concept, but the xy the dx dy still hold.
Yeah.
Top bottom sides you're crawling along x, left right you're crawling along y. Okay, yeah. Circle integral though, That was definitely much difference. Oh, first of all, obviously, you gotta convert to Cartesian coordinates. I didn't try,
To convert to Cartesian?
or it's easier, at least the way I did it, for circular integral. And the reason I'm saying that is because, is the way I set it up. So obviously, you can solve a line integral the way I just said, you basically break it apart and integrate, which honestly, that could work. Just make sure your answers match if you try that method. But the method I did was different.